Here I have a spring which is currently unstretched, and I'm going to apply force to it, causing it to stretch. And as I extend it more, the force that I need to apply gets larger. So towards the end, it gets more difficult to stretch it because the force required would be larger. Here's the force extension graph. And because work done is force times distance moved parallel to force, in other words, force times extension, I can get the work done or the elastic potential energy stored by calculating the area under this graph, which gives me this equation for elastic potential energy stored when you stretch the spring. Okay, so this equation for elastic potential energy is useful when you have the force and the extension. But sometimes you'll have the spring constant and the extension instead, in which case you're going to have to get rid of the force from this equation. So I can use Hooke's law to get rid of the force. So instead of force, I'm going to write K delta L, and I'm going to expand that bracket, and that gives me a new equation for elastic potential energy. So elastic potential energy, of course, measured in joules, the K, which is the spring constant, in newtons per meter, and the extension is in meters. Okay, what about if I have force and spring constant and not the extension? Well, in this case, I can get rid of extension by again using Hooke's law, but I'm going to make delta L the subject here, and I'm going to put that in, so F over K instead of delta L there. So if I expand this, I get another equation for elastic potential energy. In this example, I have a mass which is added to a spring such that the total elastic potential energy stored is E. Additional weights are added so the extension doubles. So that means delta L is being times 2. Assume the spring doesn't go beyond the limit of proportionality. Say the energy stored in the spring in terms of E. So the new energy stored in the spring. Okay, so it's the same spring, and also I'm going to be on the limit of proportionality, which means the spring constant hasn't changed. So we know what's happened to delta L, and we know that the spring constant is constant. However, we don't know what the new force applied is. Okay, so we need to pick one of these equations. So because we know what's going to happen to K, the spring constant, and the delta L, I'm going to use the one in the middle. Okay, so half is a constant, and the K is also not changing, it's a constant. So my delta L, the extension, is times 2, but that's inside a squared bracket. So I'm going to have to square that, so that's times 4. So the new energy is going to be times 4. So the new energy is 4E. Okay, in this example, wire A has stiffness constant K. So I'm going to label that on the diagram like this. When a mass of capital M is hung on the wire, the total energy stored in wire A is 30 millijoules. So I'm going to label that as well. When a mass of 2m is hung on wire B, it stores a total energy of 40 millijoules. So let's label that there. Determine the stiffness constant of wire B in terms of K, which is the stiffness constant of wire A. So we're trying to find the stiffness constant of the second wire here. We know if we say that the force on the first wire is M, so which is basically capital Mg, we know the force on the second wire is going to be 2F on wire B there. So which equation do we use to compare energy? So I'm going to pick one of these equations, and because I know what's happened to the force, and I know what's happened to energy, and I want to find what's going to happen to the spring constant, I'm going to use the equation which has all three of them in it. So it's just the one all the way on the right there. So I'm going to rearrange this to make the spring constant or the stiffness constant the subject. So bring the K to the top and E, the energy, to the bottom. So it looks like this. The half is a constant, so we just rub that out. And the force is being times by 2 for wire B, but the 2 is being squared, so that becomes times 4. The energy, well, the energy for wire B is a bit bigger. So what factor is it bigger by? So it's 40 over 30, which is 4/3 bigger for the energy. That 4/3 is at the bottom of the equation. So overall is 4 times. What I've done here is I've flipped over the 4 over 3 to become 3 over 4 so that I can multiply it at this. And that gives me a times 3. So the stiffness constant of this second wire, YB, is 3K.